Engineering 305, Chapter 9, Section 4. Ready to go. Sorry, we're working on continuing to understand column failure, and this lecture is about the slenderness ratio and limitations on the Euler failure equation. Equations, no new equations. I mean, realistically, it's still the same equation. It's going to be that the critical load is equal to pi squared EI over L squared, or one of the variants of that's the equation that we're working with. But let's look at that equation carefully. What does the curve of that Euler column failure look like? Well, if I look at P critical, right, and let me write down the equation one more time because I got it memorized at this point, but you don't, and that is P critical is equal to pi squared EI over L squared. So let's look at this as a function of the length of the column. What happens as my column gets shorter? What happens as it gets really short? Well, that equation, that plot, is going to go off to infinity as this gets shorter. It goes to infinity and beyond. I mean, depending how old you are. And so if I have a very, very short column, P critical goes to infinity. Well, that's not true. That's not true because there's another way that my short column could fail, and that is just this other failure is I've got a stress, which is the stress allowable. Maybe this is my yield, or maybe it's my ultimate, but that's equal to force over area. Well, this force, that's really P critical over area. So at some point, P critical is equal to, we'll just say sigma allowable times the area, and that's that line there. That is sigma allowable times area. So this is not safe. This is bad, and this is bad. This is my good region down here. I want to know where. And and so we've got a design in the green zone, but someplace we transition, and this is the hard part. Someplace we transition from this equation to this equation. And the way we talk about this is short. This region where I'm changing dramatically is intermediate. And this is slender. And that, you go, well, how do I know what's what? How do I know which equation? Those are great questions. We're going to solve that in 2 slides. On the next slide, I'm going to show you that's how our stuff breaks. And so you're seeing this compression. This is equal to sigma allowable times the area. That's in this, it becomes a compression block. It's short. Here's our intermediate, and our data tracks that. And here's our slender. So our data, and that's the equation of our Euler curve. There you go. So the data tracks this, but we've got to figure out, I can't run this all the way out to there. I'm starting to tail off. In order to solve this, in order to address this, because that's not a good place for engineers to be, where we're making all these judgment calls, because our judgment's always open to interpretation, and if we had a failure, we really don't want to be there. The way that gets solved is codes and standards. And so from our textbook, they listed 4 different ways of looking at what material do we have, how do we design with it, and who's writing the standard. And this gets confusing too in some ways, in that here's a steel standard, here's 2 different, this is aluminum and this is aluminum, but they're different aluminums. And different aluminums have different ways of solving them. Oh my goodness. And then you have to, they define what the slender range is and they define what the compression range is. And you get a cookbook for how to solve it. Let's take a look at one example. For the wood, now this is code number 4 that we're looking at. This is from the Timber Construction Manual source. Know where your codes come from. So this is specifically what we've got. And if L over D is less than 11, that defines short. Then I just use whatever the load is for whatever the allowable load is. Sigma allowable is FC. And they should, did they define FC? Well, I got to go, actually, I have to go back to their, right here, I've got, it's the allowable stress for a short block. Okay. Then I define what an intermediate range is. And here I start looking at, here's a slender range. And they have different equations for what my allowable stresses are. But now it becomes cookbook. And you just have to work through this once or twice and you go, okay, I don't like it, but I don't think anymore. I just boom, 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 apply their equations. You still have to think when you do the math because I run into calculator issues, but they give you what you need to walk through and come up with a solution. And now you have a way to go back and say, I followed the code. I followed the code. And this, structural engineers, civil engineers, a lot of what you do is following the code. All right. So the first thing we do in axial loads is to determine the slenderness ratio and determine what type of failure we're looking at, whether it's a tall, skinny, slender one, whether it's in the intermediate range, or whether it's just a block and we're hammering on it. That's the first thing we do. There are no new homework problems associated with this or exercises. This is just learning more about the Euler equation. But don't worry, there's more to come.